Okay, before solving the problems, we will look at the theory concepts we studied so far. Okay, the elasticity is a property because of which any body uh, which is undergoing some external force tries to restore back its original shape and the size after the force is removed, external force is removed, right? So whenever the body is subjected to the deforming force, right, there will be a restoring force that is getting developed inside the body. So that is what is that's what is important when we consider the body as elastic. Okay, so it's called as elastic nature. All right, then because of this elastic nature, we have basically two kinds of forces. The first one is called as a stress. Okay, stress is that restoring force which is developed inside a body, which is subjected to a deforming external force, right? But this is measured per unit area. In a sense, you apply some force on a body, the body develops some force internally per unit area. How much force is developed in 1 square meter is called as a stress. Okay, so that's the definition of stress, right? But since it's a internally developed force, okay, so we have the stress coming up. Stress magnitude and opposite in the direction of the deforming force. So you see the force developed will be equal in magnitude, but it is equal to force Newton per meter square. So it's force by area. So force is given as Newton per meter square. Area is defined in meter square. Okay, so because of that reason, you can see that the stress is denoted as force per meter square. After that, we have the strain coming into picture. So you can see that the strain is the ratio of change in the dimension of a body to the original dimension. So because of the external force, what is the amount of change that happened in a particular dimension? Divide that by the original dimension of the body. That's called as the strain. So we can understand that this strain is unitless quantity. Why this is unitless quantity? It's obvious because we are dividing two different quantities of same unit. So units will get cancelled. You have a unitless quantity coming into picture. Okay, so that's the simple reason. Now, moving on, we have different types of stress coming into picture. So what are the types of stress? First one is a normal stress, right? The normal refers to the direction in which the force is applied. So if a force is applied normal or perpendicular to the cross-sectional area of a body, right, then we understand that the force which is developed internally is also opposite to that direction. It's a normal direction to the surface area. So because it is normal to the given surface area, we call this as the normal stress. Again, since it is a stress, it is always measured as the internal force developed per unit area. Okay, so since it is longitudinal, you can call it as the normal or longitudinal stress. So we had looked at one diagram where we can see that there is a wire of certain radius and we have kept the area, right, perpendicular to the normal stress. So initially you have a length L, but because of the internal stress developed, you can the length changes by delta L. All right, then moving ahead, we have the second type that is called as the shearing stress. So what is shearing stress? Shearing stress is nothing but uh, we first try to develop a shear, in the sense the tangential force. Okay, so because of the tangential force, which is actually, it's like you have a surface and you applied a force which is tangent to that curve, okay, or that surface. So tangentially you apply a force. So if that force is applied, there will be a deforming force. That's what is called as a deforming force, applied parallel or tangential to the surface. Then internally there will be a restoring force. Okay, since it is a stress, the amount of restoring force per unit area of the object, how much is the stress developed per unit area, okay, inside the object, is called as, right, the shearing stress in this case, right? So you can see that in a diagram here. The diagram is showing that original structure is being shown as in the blue color. You can see that there is a cube which is present, but because of the application of the tangential force shown in the direction is towards the right side. What happens here? The upper surface moves right, in a sense the body will tilt to the right, so by a direction, by an amount denoted by delta x. So this is called as a shear. Okay, so this force developed internally to restore it back to the original position per unit area of that object is called as the shearing stress. Okay, after the shearing stress, we have the types of strain in a body. So we'll look at what are the different types of strain in the body. Okay, so first one is called as the longitudinal strain. So before looking at the types of strain, first let's recall what is a strain. Because of the external force, there is slight deformation of the body. And when you say that there is a deformation happening for a given body, it is definitely, right, change of shape takes place. Now, how much the change in the one dimension that happens to the body to the original dimension, that ratio is what is called as a strain. It is a unitless quantity. So longitudinal strain, if you want to calculate, then this longitudinal strain is change in the length of that object to the original length. That ratio, if you take, this is called as a longitudinal strain. Okay, so if I denote the change in the length by delta L and the original length as capital L. So if that is the case, so this delta L by L denotes the longitudinal strain of the body. Then we have second strain coming into picture. This is called as a shearing strain. So what is shearing strain? It is once again a ratio of change in the length or displacement with respect to the right original dimension. That's what we need to calculate. Now let us say that because of this shear, right, what happens? There is a displacement in the upper surface of the body by delta x. Corresponding to the height of the object, this changes. That's why we take the original dimension as the height. So shearing strain can be directly calculated by using the following formula. So you can see that it is delta x by y, right? But if you go back to the diagram and understand what is this. So if you do delta x by y, that is a tangent of this theta. So theta is a small angle between the original position of the side of that object to the current side. So there it makes an angle, right? So that angle, right, is measured in terms of this. That's what is theta. So now I can see that delta x by y, what we are writing here, this is nothing but the tan of that angle theta. But for small angles, small theta values, tan theta is equal to theta. Even some of the textbooks will definitely mention this is approximately equal to theta. So we should not get confused with that. Okay, then proceeding further, we have another type of strain, and that strain is called as volumetric strain. So let us say that there are forces applied normal to the surface of a body in all possible directions. So because of these forces applied in all the possible directions, the volume of the object will change. So originally you might have some object, some value of the volume, maybe that is capital V, but after the forces are being applied to this system, right, the whole volume will be delta. So V is the original volume, delta V is the change in the volume. So you can see that, right, the ratio of delta V to V is called as volumetric strain. It's obvious because I have to use the change in the dimension to the original dimension to calculate a strain. All right, then we studied about Hooke's law, right? It states that within the elastic limits, if you are considering the ratio of the stress inside a body to the strain, it's going to be a constant. So the ratio of stress by strain of a body is always a constant, and this constant value is also called as modulus of elasticity or elastic constant. So we have the various names coming up for this. Then, depending upon what type of stress and strain you are considering to calculate the constants, right, we have different types of names given to the constant value. The first one is called as Young's modulus. So Young's modulus is denoted by capital Y. That's the notation for this. It's actually the it can be calculated by taking the ratio of the longitudinal or linear stress to the linear strain of that body within the elastic limits. Right. So we know that Y can be denoted as F by A, force per area, whole divided by delta L by L. So both are in the same unit. So denominator will not have any unit now. Only the numerator has some unit. This is the unit of Y. So numerator has a unit Newton per meter square. So the Y or Young's modulus also gets the same what you call it's also going to get the same unit. Okay, then proceeding further, then what is the physical significance of this Young's modulus? So we can say that when I try to first let's do an experiment and let's find the Y value of a particular material, say metal. Okay, when you find that value Y of a metal, and let us say that we get a value, you can get a small value or you can get a very large value. So when the value of the Y is large, right, it means, what's the meaning of that? You need a very huge amount of force to get a small change in its dimension, in the sense length. So in order to increase the length of a metal by maybe very small, maybe 1 millimeter, you might have to apply a very huge amount of force. So that is the meaning of the Y being large. At the same time, this is also going to imply that if at all the Y value you find for a given material is very less. So in that case, it represents the total force that you have to apply to that object or that metal is very less to get a smaller change in its length. Okay, so always Y talks about how much force do you need to apply, how much force needs to be applied to get a small change in the length. Is it small or is it large? So the examples which we have written here are iron, steel, copper, aluminium, etc. So you see, it's they all of them have very high value of or very large values of Young's modulus Y. It is because they are metals and small forces will not change anything. Only when you apply this to a huge force, right, there will be change in the dimension. Then we studied about the rigidity modulus denoted by small letter n, right? So this is again a ratio, but in this case you take the ratio of shearing stress to the shearing strain. So when you say shearing stress, right, it is the stress developed because of shear force inside the body. Then shearing strain is always we have seen that it is denoted by tan of the angle theta. Okay, so in order to get an equation for this, right, we'll write N is equal to F by A, force per area in terms of the shearing stress, whole divided by tan theta, right? We already discussed that for very small angles of theta, what happens? Tan theta becomes equal to theta itself. So when tan theta is equal to theta itself, you can see that I can replace this function, this expression as F by A whole divided by theta. Okay, so we can say that the measurement can be done with the units Newton per meter square. After that, we'll proceed further to the next constant, right? It is called as bulk modulus. So normal stress to the volumetric strain, right? You calculate the normal stress in the sense in one direction, how much is the stress? Divide that by the volumetric strain, the ratio of change in the volume per volume. So that means I can definitely write this as force per area whole divided by the change in the volume per volume. So this is going to be once again measured as Newton per meter square. That's all. That's the definition and the equation corresponding to what is called as K or bulk modulus. Okay, then moving ahead, we have a, a ratio that's called as Poisson's ratio. The notation for Poisson's ratio is sigma. So what is the significance of the sigma? It's actually, if you look at the value of sigma, you will come to know that what is the ratio of lateral strain to the longitudinal strain. So how much strain you have perpendicular to how much strain you have longitudinal. Okay, this is what is this ratio. So for any given object, if you measure the sigma value, you get to know, right, which one is bigger. Is it the lateral strain or the longitudinal strain? Okay, right. Now, so this is measured, the sigma is measured by using two values, one is beta and one is alpha, and you need to take the ratio, that is beta divided by alpha. So beta by alpha is going to give the sigma value. So what is alpha? Change in the length per unit length in the direction of stress, because it is longitudinal. But when you look at the beta is also going to be very similar, but it's the change in length per unit length perpendicular to the direction. Why it is perpendicular? Because we are looking at the lateral strain. So two things we have. So using these two terms, we can calculate the sigma value. Okay, so after the Poisson's ratio defined, then we went for expression of the bulk modulus using alpha and beta. Our intention is to calculate, represent the K in terms of alpha and beta of the given body. So here you can see that we considered a specific cube, and let we assume that the size of the cube is 1. So when I say the size of the cube is 1, it is obvious that each of the sides should be 1, because when the side is 1, so length is 1, breadth is 1, height is also 1. So 1 into 1 into 1, you get the volume of the cube also as 1 only. Okay, that's why it's necessary to keep the volume of the cube as 1. And also you can see that uh, there are stresses, in specifically tensile stresses, along all the three possible directions, in the sense x-axis, y-axis and z-axis. And so those stresses are denoted as Tx, Ty and Tz respectively. Now the basic characteristic of such stress is that, let us consider one of them one by one. Initially, let's say we are talking about Tx. So Tx means what is the change in length along the x direction. In this case it is Ox, and right, corresponding compression with respect to Ty and Tz along Ox. So the meaning is that when I consider a cube and I apply all the three forces like Tx, Ty, Tz along x, y, z axis respectively, the Tx, the stress along x-axis, tries to increase the length of that cube along x-axis. Okay, but the other two forces which are acting, other two stress along y and z axis, namely Ty and Tz, they try to compress the whole object or reduce the volume in the direction of x, because y will try to increase along y, z will try to increase along z. So along x-axis, both of them will try to reduce. Okay, so that is the overall idea. Same thing can be applied to Ty. So Ty will try to increase the length along y-axis. But when you consider y-axis and Tx and Tz, both will try to reduce the length along the y-axis. So if you're talking about a particular axis, say x-axis, Tx will increase, Ty, Tz will reduce, will decrease. Same thing. If you are looking at y-axis, Ty will increase the length, Tx and Tz will reduce. Very similar to that, if you consider Tz, what happens in Tz? The dimension will increase along z-axis, but x and y axis it's going to decrease. Ty and Tx will decrease the dimension along z-axis. Okay, after that we calculated the Ox, Oy and Oz. Okay, Ox we try to represent using the following format. So the format is Ox is written as 1 because 1 is the initial length, and Tx will increase the length, so this is plus alpha into this. Why alpha? Alpha is the coefficient along the same direction, and beta is the coefficient perpendicular to that direction. So for x-axis, y and z-axis are perpendicular. That's why. So beta times Ty and beta times Tz are subtracted from 1 plus alpha into Tx. Okay, that's the actual length now along x-axis. All right, after that we have Oy. So Oy, in the sense, the one force that is being applied and that tries to increase the length is Ty. So 1 plus alpha times Ty minus beta times Tx minus beta times Tz. So Tx and Tz will try to reduce the length Oy. That's why they are being subtracted. Very similar to that, we have Oz written as 1 plus alpha Tz minus beta Tx minus beta Ty. So this is because alpha Tz will increase the length along x-axis, beta Tx reduction, beta Ty is also reduction. So both of them will reduce the particular axis, right, by a specified amount. So you know that alpha is the linear and beta is the lateral. Okay, now in order to find the volume, I need to multiply all the three terms. So three terms are Ox into Oy into Oz. So substitute and simplify, and when you simplify, you get the answer is equal to 1 plus alpha into 2 beta into 3 times t. Okay, no, but now our intention is actually to calculate the k value. So what we do, we look at the change in the volume, which is initial volume minus final volume. So if you consider this particular diagram, right? So initial volume is actually 1, and the change in the volume is, sorry, the final volume is 1 plus alpha minus 2 beta into 3 times t. So it is obvious that 1 will get cancelled, and after that we are left with alpha minus 2 beta into 3t. Okay, that is the change in the volume. So using this, we can actually find the bulk modulus. K is equal to 1 divided by, right? Sorry, it's a T divided by T divided by alpha minus 2 beta into 3T. So T and T will cancel. So we are going to have the answer K is equal to, which is the required bulk modulus, is equal to 1 divided by 3 into 1 minus alpha minus 2 beta. That's the final answer we were looking for. Okay, then let's move on. Moving further, the next concept that we are actually looking for here is the expression for Young's modulus, that is y. So let's look at the definition. What is Young's modulus? Young's modulus y is equal to whatever longitudinal stress you get, whole divided by the longitudinal strain. So the stress is capital T and longitudinal strain is given by alpha times T. So you see that y is equal to T divided by alpha T. So that is nothing but 1 by alpha. So using this equation, y is equal to 1 by alpha, we can calculate the y value of a given object. Okay, so this is important. Will be used in many problems at a later stage. Okay, then we go ahead and calculate the expression for the rigidity modulus. So in this case, let us consider a cube, right? So the front face is denoted as A, B, C, D. And let us assume that the face on which you mark CD, that particular face is at the bottom and AB face is at the top. Okay, so under this condition, right, we have there is the it is attached. The bottom surface is attached to a surface, so it is not, you are not allowed to move it. At the same time, the expanded or the top surface, what you see there, it is exactly not exactly connected to any side. So because of this, we can also write it as say by the application of the tangential force at the top surface will get right, it gets shifted to right by certain amount, right? So that amount is denoted by L, which is, you can see it is marked over there. The force capital T will bring it to the right. So how much is the distance that it has been taken now? So if x is the length of the subject or the object which we are finding, so this L is actually the shift in the length. Okay, then let's try to denote the theta now. So theta is the angle, right? You can consider this as the angle by which the B moves to B dash. So what we do here, we calculate the theta value direct. So this is the theta equals to BB dash. So on the top we can see that there is a BB dash. So BB dash I should divide by BC. BC is the height of the cube. So BB dash is equal to L and BC is the height. So height is denoted by capital L, as we originally discussed about the particular ratio, change in the dimension per original dimension. Okay, now uh, if at all we want to calculate the tangential stress, then it will always be equal to the okay, so the shearing stress. So tangential stress always equal to the tensile stress capital T along BD, and it will always be compressive along AC. So obvious, because AC will be reduced. Okay, the length AC will be reduced when it moves to right, and the BD will be increased. Right, so we can see that I have already written here. So because of this tensile stress, BD, diagonal BD will increase, right, by an amount MB dash. At the same time, the other diagonal will reduce. So if we consider the same notations, alpha for linear strain and beta for the lateral strain, we can calculate the strain along the BD. That is capital T into alpha plus beta. So MB dash by BD, if we want to represent that mathematically, referring to the given diagram. Right? Now let us calculate MB dash. So from the diagram, it is very clear that you can calculate this as BB dash into cosine value of B angle BB dash into M. So it's very clear that the given diagram there should be having a value of 45 degree as BBB dash M. So this means the final value we can write it as L by root 2, BB dash by root 2. So it will be L by root 2. So we can calculate the angle using this formula. Whatever is length L, divided that by root 2. So if you want to calculate now T of alpha plus beta, so this should be L by 2 divided by capital L by 2. So each of them have different values. So when you try to cancel this out, L and capital L are as it is. Other terms, you can see that the theta and theta will get you are going to multiply them and write them as follows. Okay, so that's how we always calculate the rigidity modulus. Okay, so T of alpha plus beta is theta by 2, which means how do you calculate the n value? N value is nothing but capital T whole divided by theta. So already we had a theta over there. So in order to cancel that, we'll do the 1 divided by 2 times alpha plus beta. This is called as the rigidity modulus, that is denoted by n. All right, then we'll move on to find the relationship between the y, n and k. So in order to find this relationship, let us start with the equation of k. So just now we calculated each and every value, that is y, n and k. We need to make small modifications so that we can relate each other. So first we start with the k equation is equal to 1 divided by 3 into alpha minus 2 into beta. This is also equal to, I can take a alpha outside, so 3 alpha into, this is 1 minus 2 times beta by alpha whole raised to the power, right? Whatever the value we have taken, you can write that. So k is equal to y divided by 3 times 1 divided by, that is 2 sigma. So beta by alpha, so if you take this beta by alpha, which can be replaced as sigma, I can see that the k can be written as y divided by 3 into 1 minus 2 sigma as the equation format. So then we have y by 3k should be equal to 1 minus 2 sigma. So by simply reshuffling the above equation, we get this, and we call that as equation number 1. Okay, so we got one equation from the equation corresponding to K. Right. Now we move on and we calculate the n equation. Okay. So how you calculate that? N is nothing but 1 by 2 times alpha plus beta. So alpha plus beta, I can try to take the alpha outside. So that makes 2 into alpha into 1 plus alpha. When I did try to define alpha as, so we have multiple options here. First one is, how do you represent a real number? That's x of n. If you have something like that, how do you represent? So you can see that this is equal to 1 divided by 2 times alpha plus 1 minus 1 plus sigma. Then I try to write it in the following fashion. This is equal to y divided by 2 into, I try to write it as y divided by 2 into 1 plus sigma. So take n to the other side and the denominator to be brought to the vacant space. So in such cases, y by n is 2 plus 2 sigma, y by 2k is 1 plus 1 sigma. Okay, now, so this means you can see that the y by 3k becomes equal to 1 after I add the two equations, because equation 1 and equation 2 are as shown over here. We'll write one below the other and simply we try to add. Okay, so but before that we need to take care that whenever you add the two terms, the sign of the second object will change. So only because of that reason we get the answer y by n plus y by 3k is equal to 3. So 2 minus 1 is 3. That's what I, sorry, 2 plus 1 is equal to 3. Okay. Then let's move on to the next topic. So here we are going to discuss the end point where this alpha has a limit. Okay, now we know that this 1 minus 2 sigma is the denominator of the given expression. It expects us to have each and every terms. Okay, so 1 minus 2 sigma has to be positive. Okay, so now which means I equate that to 0. 1 minus 2 sigma. Yeah, 0. So 2 sigma should be less than 1. Sigma should be less than half because I move the 2 to the other side. And when you have the value as half, which is 0.5, this is the condition for sigma. Maximum value of sigma should be 0.5. If it crosses, the term becomes negative and you don't get the specific or the required value of 1. Then moving ahead, we have the concept of torsion of a cylinder. So torsion of a cylinder in the sense the top of the cylinder is fixed, bottom of the cylinder you apply a couple so that bottom will rotate. So this rotating effect is what is called as torsion of a cylinder, right? So we will go quickly about this. Now in this case, in the torsion part, so we know that there is a cylinder whose radius is r and length of the cylinder or height of the cylinder is denoted by L. So you always write a equation for we write an expression first, and we apply the twisting to one end of the cylinder. So let's say the bottom of the cylinder you apply this, right? So because of this, let us say the bottom of the cylinder rotates by a given amount. So that should be theta is equal to, this is alpha. So now theta is the angle of twist. B dash is equal to x into theta because x is the radius, and we have theta as the angle measured. So x into theta gives me the circumference, that is L into phi, because phi is the angle made at the top. Okay, so using that we can directly measure the required B dash. Alright, this implies I can actually calculate the phi, right? The phi can be calculated as x into theta divided by the height of the cylinder. So we'll hold on to this equation and we call the equation by number 1. Then if delta F is a tangential force, then we can calculate the tangential stress by, that's the equation. The force is delta F and area is equal to 2 pi x into dx. Right. So because of this, we can directly write in the required format. Okay. Now moving ahead, using this tangential force, we can directly write the rigidity modulus. And the rigidity modulus can be calculated as tangential stress, which is just now we have calculated, divided by, so we divide that term by this one, the shearing strain. So just divide one by other. So the equation number 2 divided by shear strain is denoted by 5. Correct? So we can simply write it in this fashion. Okay. So as a result, so we can calculate the delta F. So delta F is nothing but the amount of force that is required. So directly we can write the force in this method. So delta F becomes equal to 2 pi n phi into dx. We are simply rearranging the terms. Okay, then let's go to the twisting couple because our intention is to calculate the couple at the end. So first we go for the twisting couple. Okay, so the twisting couple is straightforward. It is tangential force into the distance. Distance here is x, right? So we can represent that using this notation. So overall, I get a delta C is equal to 2 pi n theta by L into x cube. Okay, so that's the representation, right? But if you want to calculate the total couple, I should integrate. So how the integration takes place? It has to be, right, 2 pi n theta by L and integration 0 to r, because x is minimum value is that minimum value of x is 0 and maximum value of x is r, right? So because of that we have the representation in this fashion. Now you perform the integration of x cube becomes x power 4 divided by 4. X power 4 by 4 is what we get. Now as a result, next you can see that the 2 and 2 will get cancelled in this case. So once we cancel the 2 and 2 here, you can see that we get the answer of C as C is equal to pi n r to the power 4 by theta by 2L. So that's the required equation. And then we have the next concept called as torsion pendulum. So in torsion pendulum, we are looking at the twisting of a cable connected to a pendulum. So here we are considering L as the length of the wire and R as the radius of the wire. So this wire is connected to a fixed end at one side, other end is connected to an object. So you twist the object, the wire gets twisted. Okay, so and when you release it, there is a special kind of oscillations. So first it will rotate in one direction, then it will rotate in the other direction. So that actually creates what is called as torsional oscillations. So we have the torsional oscillations coming into picture. So we try to denote the following things from the diagram. First one is I, which is the moment of inertia of the body about the given axis, right? So this is a special feature of a body and its mass, because of which it tells how difficult it is to make that object to move when it is at rest. That is I. Okay, then T is the time period of oscillations. What is the duration of one oscillation? Then C is the restoring couple per unit twist. Whenever you twist the object, there is a internal force, internal couple that arises to restore the whole process. Then theta is the angle of twist. So if all these quantities are known, then we can definitely perform what is called as, and we can relate the I, theta, C and T like this. So the equation to relate them is I into d square theta by dt square is equal to minus C into theta. So bring C into theta to this side and divide by I. So that gives you equation number 1. We hold on to this. But when we look carefully, we understand that this particular equation is nothing but it is a harmonic oscillation, simple harmonic motion. So whenever you know the simple harmonic motion, we can always try to calculate its time period, capital T, as 2 pi into root of pi by C. So we rearranged it and we get the equation of C as 4 pi square I by T square. Very simple equation. And after that we have what is called as the bending of a beam. So here we discussed about a beam, and when you apply a force to one end of the beam, what exactly is going to happen? So beam will bend, right? So whenever the beam bends, right, you can see that in the diagram we have applied a weight W at one end so that it gets bent. BC, which was actually straight with the AD, has shifted down. Okay, so that is what is the concept. All right, now moving ahead. So we always will consider the process of bending of a beam like this. So whenever you apply the force to a beam, we assume that the beam is made up of several sheets or filaments. So you can see on the right side diagram, the given beam is straight. Okay, there are two filaments, but when you apply the force, beam bends. The outer side becomes convex, its length will increase, and inner side will decrease, it becomes concave. Okay, so we use this concept when we apply the load to this. So obviously from the diagram it is clear that the outer side has increased, so B dash C dash is bigger than AB. At the same time, the lower filament was decreased in the size. So when we say it is decreased, it's obvious that, right, C dash D dash is reduced. So it is reduced by the specific amount. Okay, all right. Then in this case, you can see that the EF is given by R into theta, right? So R is the radius, theta is the angle subtended at the center. At the same time, if you want to look at the outermost side, then I need to add Z to R. So this becomes R plus Z into theta. So perform that R plus Z into theta to get this value. So what is the strain? It is change in the length divided by the original length. Change in the length is Z, original length is R. So Z by R is what you get at the end. Then you can calculate the Young modulus by delta F by delta A whole divided by Z by R. So we can reshuffle this to get the delta F is equal to YZ delta A divided by R. So we get that first. Once that is done, then our next objective is simply to calculate this, that is bending moment. So bending moment is summation of the whole force, that is y delta A z square divided by r. Y by r can be taken out. Whatever is remaining inside the summation is called as the Ig. Okay, it is the moment of inertia. So final answer, bending moment is Yig by r. This is what is the importance of this particular derivation. And then we have Young's modulus of a cantilever. So cantilever, you can see that it's actually a beam with one end loaded. So you see that the shape is not straight, shape is little bit curved. So we have the, with respect to that diagram, let us say the length of the cantilever is L, delta is the deflection at the free end, how much free end has moved with respect to the original position. Then consider a small length of the given cantilever, we call it as dx. Then x is the distance of that position from the origin or from the fixed end. Then radius is denoted by capital R, and we have dy as the deflection of the PQ. So overall, considering this, now we can write the standard radius of curvature can be represented as r. Then 1 by r has this equation, that is d square y by dx square whole divided by 1 plus dy by dx whole square whole to the power 3 by 2. But what we do, we approximate this to only numerator because denominator is assumed to be a dy by dx to the powers will be assumed to be a small quantity. So then what is the moment of force? It is force into distance. Force is W. Distance is total L minus X. So L is the total length out of which X has been subtracted to reach the point. So that's one thing. And I need a couple. So what is the internally developed couple? That is Y, which is Ig by R. Okay, we call that as equation number 3 now. And after that, you can see during equilibrium, both the forces have to be equal, right? So I equate both of them, Yig by R. So where the 1 by R is d square y by dx square is equal to W into L minus X. Okay, so W into L minus X will always give me Y into Ig integration dx is equal to W into integration L minus X dx. Okay, so this means I can always write integration of d square y by dx square is dy by dx. Okay, so you can see that it has been updated as dy by dx, and on the right hand side I have L becoming Lx, x becoming x square by 2. So call it equation number 4, and we find the value of C by equating it to x equal to 0. When x is 0, dy by dx is 0. Obvious, because at the leftmost side, when there is no movement, right, you don't see any change. So deflection is 0, so rate of change is also 0, right? C becomes equal to 0. Update that in the above equation. Now I need to calculate the value of y, means I need to eliminate the dy by dx, right? How do you eliminate? Simply perform the integration. So integration y is with respect to 0 to delta. Y axis, the movement is 0 to delta, as x is moving from 0 to L. As I move along the cantilever from length 0 to L, the y varies from 0 to delta. That's what is the meaning of this. And we simply solve this particular equation, and at the end you can verify that the equation that you are going to get for y is equal to